Recently, the database community has been doing substantial research on so-called collaborative data management system. This is great, and I think we have recently found a new interesting perspective that our community should explore. In this video, I will tell you what it is. Hey, my name is Mohammed from the Technical University Darmstadt, and this is joint work with my collaborators Sam and Carsten. In this talk, we will explore the research on database management systems for data sharing and raise new and interesting questions that we think our research community should have a look at more closely. Now, let me be completely honest with you. I will not present answers to these questions, but make sure to stick around until the end of this video because I will share with you what we have been working on to come closer to answers. If you listen carefully, I'm sure you have noticed that I used two terms so far: collaborative data management systems and data management systems for data sharing. So, is there a difference between these two terms? No. For the purpose of this talk, we will treat both terms as synonyms. However, I think this is already an interesting question. What is the correct terminology in our context? Let me know down in the chat what terminology you prefer and why. Personally, I prefer the term collaborative data management systems. To explain why, let me clarify the context and the setup with the help of an analogy. How did people collaborate on documents in the past? Not too long ago, people wrote the document, printed it, and sent it via email or fax to collaborators to get feedback. Incorporating the feedback was, of course, a manual and time-consuming task. With the invention of email and modern web processors, this process got much faster. Instead of printing and sending via fax, we could simply create a copy of our document and send it to collaborators. They would then comment on the document or make changes and send us a new version back. Already back then, it was super important to be able to verify what others changed and to be able to accept or reject their changes. In fact, even the early versions of Word for DOS included this feature. Nowadays, collaboration on documents became even smarter, because we do not need to work with copies at all. With the help of tools such as Google Docs or Overleaf, we can create shared documents and co-author the documents live. With other words, collaboration became instant. Now, let's project this experience to databases and data management. Where are we there? I'm fairly confident we passed the fax era, but are we past email? I believe not, at least not yet. How collaboration on data works today is very similar to document collaboration in the email era. Everybody maintains his local database, and in order to collaborate, we create a copy of some data and send it to our collaborator. The receiving party can then verify the data, transform it, and incorporate it into their own database. With the help of our analogy, I think the next step is very clear. Instead of sending copies around, let's create shared databases that organizations can manage collaboratively. And managing data is of course not limited to read-only access. It's also about updating data and inserting new data into the shared database. Whoa, hold on, no way. You want to give third parties direct access to our mission-critical system? You cannot just do that. Yes, you're right. With the current database management systems, we cannot just do that. They were designed for being used by a single organization only, and they do not include mechanisms to track and verify if and how collaborators change the data or the database. Of course, there are also other important aspects and requirements besides verifiability, but our focus today will be on the verifiability aspect. Speaking of verifiability, we can distinguish two common guarantees that collaborative database management system must provide and must be able to verify, namely the integrity of transaction execution and the integrity of data. The goal of these guarantees is to govern the shared database. That means to guarantee that data is only modified and accessed based on a predefined and agreed upon logic that everybody adheres to, and that no party can tamper with the data in a different manner. If we now look at how the existing systems that I mentioned before implement the verifiability guarantees, we can observe that these systems typically take an implementation-centric approach. FalconDB, for instance, uses blockchains and authenticated data structures to implement verifiability. It also uses an incentive-based scheme where nodes are encouraged to verify the execution of queries asynchronously in order to hide the verification cost. As a result, however, this also means that potentially unverified queries from malicious servers stay undetected. In contrast to that, updates are always verified synchronously for the entire network. Yet, another system might choose to verify also updates asynchronously. As you can see, you always opt in to certain guarantees by choosing a particular system. Let's contrast this with the asset guarantees of classical databases. Here, the concrete properties that should be satisfied can be defined declaratively and are implemented by databases in various ways. As an example, for the isolation in asset, a user can declare the specific isolation level that a transaction should run under. This isolation level is then guaranteed by the database through an optimistic or pessimistic concurrency control scheme, for instance. Our proposal is to apply the same concept to verifiability. That means, similar to the other components in asset, let us enable the user to specify the degree of verifiability declaratively using different verification levels. We think this approach fits nicely into the asset model and enables us to build database management systems for shared databases that decide based on the verification level what optimizations and execution strategies are best suited to meet the desired guarantees. Let me explain to you in more detail how this could work. For that, let's look at the life cycle of a transaction in a classical database with the help of this simplified state model. As you can see, once a transaction has been processed, it is either committed or aborted. And transactions that reach the committed state are guaranteed to fulfill the asset properties. An interesting observation is here that this state model allows us to reason about different isolation levels. For example, in the read uncommitted level, transactions are allowed to read the state of other transactions that have not committed yet. Under the read committed isolation level, in contrast, transactions are only allowed to read committed state. We believe that extending this classical state model can help us to reason about these and similar questions. That's why we propose to extend the state model of asset-compliant database management systems with a verified state. Like this. Modeling verified as an additional state that follows the committed state has several advantages. First, since verification is typically an expensive task, the model leaves some freedom for when the transition from committed to verified happens. That means it could be directly after the commit, or it could be deferred. Moreover, it enables the user to declare which state is allowed to be read by transactions, similar to what is done for isolation levels. For example, we can control if transactions can read committed but unverified state, or if the state has to be verified before it becomes visible. Lastly, since the verified state is only an optional state, we might as well allow that not all committed transactions need to be verified. This would enable optimizations such as partial verification to reduce overhead. Similar to isolation levels, depending on the concrete setup, different things could go wrong. However, let's not focus on the bad things for now. Instead, let us see how we can define different verification levels with the help of this model. I mentioned three different aspects that our simplified state model could express. First, whether verification is mandatory or not. Second, when does verification happen? And third, what state is visible to a transaction? And this is how we can use these three aspects to define verification levels. We could define a strict verification level in which verification is mandatory and directly follows the commit of a transaction. This nicely describes the current standard view on verifiability. That is, transactions are only committed if they have been verified. Alternatively, we could define a less strict verification level in which verification is still mandatory but may be performed asynchronously. This makes room for different optimizations. Most importantly, transactions are not blocked by potentially expensive verification protocols, since verification can be executed in batches or in a deferred manner. This is similar to deferred verification schemes that are available in existing systems such as Veritas and BlockchainDB. The last level that I have prepared is an unstrict verification level, in which verification is optional. This is very similar to the previous level. However, the database management system would not enforce that transactions are verified. Instead, the user could explicitly request to only verify a subset of transactions. This in turn allows us to limit the overhead of verification to some, for example, important transactions, or to provide probabilistic guarantees by only verifying a sample of transactions. This would be similar to the query verification scheme of FalconDB that I have mentioned earlier. I'm pretty sure that you have many interesting pressing questions by now. In fact, I also have. What happens if verification fails and malicious activity is detected? How does recovery look like? And do we need recovery at all? Does it depend on the verification level? And do verification levels cover all the different dimensions of verifiability that we mentioned earlier? All good questions, but as I mentioned earlier, I won't present solutions today. Instead, let me know in the chat or in the QA sessions what other questions come to your mind. And feel free to reach out and let me know what you think about our AcidV transaction model. Now, before we close, I promise to share with you what we have been working on to come closer to answering some of these questions. Our group is building an AcidV-compliant collaborative database management system that is called Trustable. We are building Trustable with a clear focus on data sharing and collaborative data management in mind, and experiment with different techniques to implement verifiability guarantees. Feel free to check out the project website and follow us on Twitter and LinkedIn to stay up to date about the project. Also, if you have interesting ideas or use cases for collaborative data management, please reach out to us. We are always looking for collaborators and people to join our team. With that said, thanks for watching, and I'm looking forward to your questions in our discussion. Take care.